So let me talk about change briefly. I guess there's two basic approaches. One can do sweeping change and one's radical big hit, which I'm absolutely all for, or maybe we can change in steps within the system. And that's a question I've been interested in. I feel like I really get what Conrad is saying, and I'm totally and absolutely up for it. But to be honest, I'm going to say that I think we should expect some serious resistance. Having worked in the school systems now for 10 years, I know that, as we mentioned yesterday, teachers are emotionally afraid of change. And it's all a matter of confidence, and change is going to be scary. It's going to absolutely be scary. So I'd like to give some thought and attention to the second approach. Can we make some baby steps, at least, in the right direction and prove that computer-based math is actually something worthwhile that's actually accessible even to the teachers? So let's take a quadratic, a topic that's just come up multiple times. Let's talk about quadratics. So as a thought exercise, I said, okay, let's take something very standard, very labored in the curriculum, and how can sort of computer-based thinking come into something of this ilk? Teachers are going to resist this in many ways because, okay, they might look at something like the randomness module that we saw yesterday and say, that is fabulous, it's wonderful, it's very nice. However, I need to be on page 423 of the textbook by next Thursday, and the state exam says I need to be there, and that's not going to change. Well, good, I have to teach these formulas. I do teach quadratics. My kids can do all that on the top part of the screen, but they have not memorized a single formula. They've seen the quadratic formula, but to them it's all about, I teach the conceptual process. They know where the vertex is without having to do anything. They know how to work out the roots of a quadratic without having to actually memorize the equation. That equation is not on any of our cheat sheets for the exams. So what I really think we should ask is, why is this material in the curriculum in the first place? What was its initial intent or design? And maybe curriculum designers might say things like, there's some mathematical sophistication to be gained from really looking at one topic in some depth. And quadratics are rich. And they're important, they appear in nature all the time. Though what's very scary to me is that those connections to nature are often mentioned in textbooks, not actually explained why they're there. You can fold a piece of paper and see tangent lines in a clever way that turn out to be a parabola, but why is that true is not often the case. Also, you see I've mentioned U-shape up there. I didn't say parabola. A lot of books will say it's a parabola, these quadratics are parabolas, but they'll never make the connection to the Greek geometry. They just say it's assumed all U-shaped curves are the same. Quadratics, they're inherently interesting. Why not study them? It's great. Unfortunately, I think some teachers will say that we need to study quadratics because they appear on standardized tests. In which case, let's memorize these formulas, let's give jargon, let's give all these forms names. I cannot stand it. I'd rather just do what's appropriate rather than just give things names first. But here goes. So I just said, okay, how can computer-based math start to transform sort of a very labored topic from within the system? So I just thought about some ideas. And one is, give real substance quadratic data to data. I mean, that's the obvious thing to do. Maybe sort of a great module would be, are all shapes the same? For example, Galileo asked, is a hanging chain the same shape as a parabola? That's a very good question. It took, a century for mathematicians to figure that out. Maybe kids could explore that with real-world data. One of the things computers do is animate, as mentioned earlier. I love it. What do you do if you change that middle coefficient of quadratic? Just play with it. Lots of fun to be had there. I don't know why calculus is put at the top of the heap in the high school curriculum. Slope is a very elementary concept. Kids can take hold of it. And in fact, if you look at slope, you're going to find where a minimum or maximum of a quadratic is by playing with slope. In fact, if you want kids to know the formula x equals negative b over 2a, which I personally have not memorized, maybe they could discover it by playing with slope. And this can go beyond quadratics. It's just the idea of a maximum occurs where the slope is 0 is very natural and intuitive. Let's have kids do that. I really think the point of quadratics is give kids a sense, intuitive feel of what a formula could mean. And these are lovely because they're symmetrical. And one nice thing about it is I always ask, what are the interesting x values in a formula? And for example, in this example, I obviously see that x equals 2 and x equals 10 are interesting. Well, voila, I have two symmetrical points, symmetrical graph. By common sense, I can see the graph must be like that. Even if the x values aren't obvious, do a little bit of manipulation algebraically, see, okay, what are the interesting x values? What can I do to this formula and just find something interesting? My curriculum has me have kids fit quadratics to 3 data points. And they're meant to do this with a quadratics regression feature on a calculator. My kids do not pick up the calculator, I'm afraid. What they'll do is they'll just write down a polynomial that fits 3 data points with ease. In fact, they're very proud of themselves. They can write down something like that, which looks scary and horrible, but intuitively understand it. In fact, if you see that works, I put in x equals 5. Will indeed 9 come out? Yes. This little Lagrange's interpolation formula. But then let's have fun. Here's the data that spells my name. J is the 10th letter of the alphabet. A is the first. I wrote down that polynomial, had a computer system just actually expand it for me, and there's my personalized polynomial. Kids love that sort of thing. It just speaks to playing. But I'm a pure mathematician, and I want to explore juicy projects. And kids like to play with numbers, square numbers, triangular numbers. Which are more of? So you make a table. And, all right, I just looked at how many square numbers are less than n, how many triangular numbers are less than n, and if you look at the right-hand column, does that ratio seem to be going to something? And a lot of kids will say, well, it looks like if the number 1.414 square root of 2. So there's a mystery. So I think we can also motivate good learning in just pure math mysteries as well as real-world mysteries. Is that really the square root of 2? In fact, I would even make this the starting point of my course. Why is the square root of 2 appearing here? And it turns out to answer this question, you get a little quadratic formula, and I'd want to know how can I find out why is that going to square root of 2? Well, I naturally want to do some algebra on it to complete the square and see root 2 is naturally sitting there. So maybe baby steps are the way to go. Maybe the way to think of as a topic is, why was that in the curriculum in the first place? How can we turn that around? And then convince teachers that it's okay, it's safe to do this. You can still get to page 423 by next Thursday. And once that's in the system, then let's do the big thing. Let's go for the radical change. Thank you.